So let us look at the following example. Suppose a 0.75 kilogram block of ice at negative 15 degrees Celsius is placed into a beverage that is at 25 degrees Celsius. So let's assume the beverage is composed mostly of water so that the specific heat of the beverage is the same as of water. Now, at what temperature and in what phase will the final mixture be, assuming that the mass of the beverage is 4 kilograms? So let's begin by taking the ice, placing it into the beverage, and then realizing what happens. So the first thing that happens is energy begins to flow because there is a difference in temperature. So because the beverage is at a higher temperature, energy begins to flow from the beverage into the block of ice. So we want to ask ourselves in part 1, how much energy is required to increase the temperature of the ice from negative 15 degrees Celsius to 0 degrees Celsius. So we want to use the following equation. The Q, the energy gained by the ice, is equal to the product of the mass of the ice, the specific heat of the ice, and the change in temperature of that ice. So we know what the mass is. It's given to be this quantity. We know what the specific heat of ice is. It's this quantity, which we can look up in a textbook or online. And we know that the change in temperature of the ice is 15 degrees Celsius. So we multiply these three values and we get 47,092.5 joules of energy is gained by the ice, and this same energy is lost by the beverage. So let's go on to step 2. So once the ice is at 0 degrees Celsius, the energy will continue to flow into the ice. But now that energy no longer increases the temperature, but rather it breaks the intermolecular bonds in the ice. So it melts the ice. And we want to ask ourselves how much energy is required to melt 0.7 kilograms of ice. So we essentially want to use the following equation. The product of the mass of the ice and the heat of fusion for the ice is equal to the amount of energy gained by the ice. So the amount of energy gained by the ice, well, we can look up the heat of fusion value for water, and it's given by this quantity. So 0.75 kilograms multiplied by 333,000 joules per kilogram, the kilograms cancel and we're left with 249,750 joules of energy is gained by the ice to completely melt that ice. So, at the same time that the ice gains this much energy and this much energy, the beverage loses this much energy. So we want to ask ourselves in part 3, what would be the temperature of the beverage after it loses this many joules of energy, and assume that the specific heat of the beverage is the same as that of water. So we essentially want to sum up these two values, and notice our Q value is now negative because the beverage loses that many joules. So negative, the sum of these two values is equal to the product of the mass, our specific heat, which is the same as water, and T minus 25. So our initial temperature of the beverage is 25 degrees Celsius, and we want to calculate the final measure of the temperature, T. So we essentially add these two, we divide both sides by the product of these, and then we solve for T. And we find that T is equal to 7.3 degrees Celsius is the temperature of the beverage after the ice completely melts. So now we have the melted ice, and that liquid is now at 0 degrees Celsius, while the beverage is at 7.3 degrees Celsius. So now in step 4, we want to calculate the final temperature of our mixture. So the energy that is lost by the beverage, which is negative, is equal to the energy that is gained by that liquid. So we want to use the following equation. So the negative of the product of the mass of the beverage, the specific heat of the beverage, and the change in temperature of the beverage is equal to the product of the mass of the ice, the specific heat of the ice, and the change in temperature of our ice. Now notice this ice is no longer ice. It has now melted, so it's liquid water. So we plug in our values and notice that the CB value and the C ice value are the same values because we assume the specific heat of the beverage is the same as water. So these values will cancel. And now we solve for our X. Notice the X value is what we want to find. It's the final temperature of our mixture. So we have negative 4 kilograms multiplied by these two cancel, so we don't have to worry about those, multiplied by the final temperature of the beverage minus the initial temperature of the beverage, which was found in part 3. And this is equal to 0.75 kilograms multiplied by X minus 0, where the 0 is simply the temperature of our ice, which is now water, and X is the final temperature. So notice the mixture at the end is at the same exact temperature. So we solve for X and we find that X is equal to about 6.14 degrees Celsius.